This presentation outlines the City of Virginia Beach's concerns with a proposal to mine uranium in the Roanoke River watershed, and presents findings from studies to estimate the potential impacts should a catastrophic event happen upstream of the city's water supply at Lake Gaston. This map shows the known potential occurrences of uranium throughout Virginia. Highlighted is the location of the only proven uranium ore deposit at Coles Hill in Pittsylvania County. The Commonwealth of Virginia has maintained a moratorium on uranium mining for more than 30 years. As this map indicates, should the moratorium be lifted, there's the potential for uranium exploration and mining throughout Virginia, not just at Coles Hill. The City of Virginia Beach and other Southside Hampton Roads localities receive water from Lake Gaston through a 76-mile pipeline extending to Suffolk, Virginia, where it discharges to Lake Western Branch. Lake Gaston receives approximately 93% of its inflow from Carr Reservoir. These bodies of water straddle the Virginia-North Carolina border and are located within the Roanoke River watershed, which is indicated by the gray area on this map. Coles Hill is situated near the Bannister River, a tributary that meets the Dan River and feeds into Carr Reservoir. Virginia Uranium Inc., or VUI, is the company seeking to exploit the uranium deposit at Coles Hill. Their available data indicate that the deposit could yield up to 120 million pounds of uranium yellowcake. The June 2012 economic assessment prepared for VUI investors suggests that approximately 30 million tons of ore with an average grade of 0.1% could be economically mined. Given this average grade, 0.1%, it can be concluded that 1 pound of uranium yellowcake would require excavation and processing of 1,000 pounds of ore. In other words, for each pound of yellowcake, 1,000 pounds of toxic waste byproduct called tailings will be produced. Processing the blasted and excavated granite rock involves crushing and grinding as well as chemical leaching of the uranium. This process leaves behind a massive amount of pulverized material called tailings, which is nearly devoid of uranium, yet still contains more than 80% of its original radioactivity. This is due to the fact that the process removes only uranium, but none of its highly radioactive decay products, such as thorium and radium. In addition, many toxic heavy metals, including lead and selenium, may be retained in the tailings. The tailings require on-site storage, typically behind earthen dams, as shown in this image from the infamous Moab tailings pile in Utah. Even though the construction, operation, and maintenance of waste storage facilities is regulated, these tailing containment cells are known to fail, causing the release of large amounts of toxic materials into the environment. The International Commission on Large Dams, ICOLD, has documented hundreds of such incidents, with releases often exceeding millions of cubic yards and traveling distances of many miles. These images show just two recent examples, one from Hungary in 2010 and one from Tennessee in 2008, both of which impacted large areas and inundated rivers and homes. Virginia Uranium has made public statements that tailings containment failures are not likely to happen because they will store the waste underground. However, as recently as June 2012, documents prepared for their investors still consider surface tailings impoundments. In addition, the question on the feasibility of storing tailings underground has never been resolved. The 1983 Union Carbide Marline study stated that below-grade tailings disposal is not practical because of the high water table. Given the history of tailings dam failures, the City of Virginia Beach is rightfully concerned about a large-scale industrial operation in the watershed upstream of its primary water supply that will yield millions of tons of toxic and radioactive waste material. In addition, while uranium mining has historically been conducted in areas of the U.S. with dry climates, the proposed mining site in Virginia is very different from the U.S. regulatory experience with respect to its climate and the potential of a tailings dam failure. A 2008 study tallied tailings dam incidents in Europe and worldwide and categorized these events on the basis of the likely cause of failure. As this graph shows, the researchers concluded that unusual rain has been the most frequent cause of tailings dam failures. This color-coded map displays the average annual rainfall throughout the United States. It is evident that the annual average rainfall in the east is about 10 times greater than in the arid west, where uranium mining has traditionally been practiced. For example, a single nor'easter in Virginia can yield more rainfall than the total annual precipitation in vast areas of Arizona, New Mexico, Colorado, or Utah. This annual average precipitation map doesn't even tell the whole story. There are other areas with similar amounts of annual average precipitation where uranium is mined, for example in France. However, unlike France, Virginia is also subject to extreme rainfall events. The geography and climate in Virginia, particularly along the Blue Ridge Mountains, can facilitate extreme precipitation events, capable of inducing massive flooding and landslides. Two events approaching the probable maximum precipitation, or PMP, are known to have occurred within the last 50 years. As described in vivid detail in Stefan Bechtel's book Roar of the Heavens, the remnants of Hurricane Camille inundated areas of Nelson County in August of 1969, with 30 inches of rain in less than 12 hours. Eyewitnesses described the rain as intense as standing under a waterfall, and mountains were literally stripped of topsoil down to bare rock by the intense rain. A similar near PMP storm occurred in 1995 in Madison County, also along the Blue Ridge Mountains. This graphic shows rainfall depths versus rainfall duration for various unusual events in the United States and worldwide. It illustrates that the two most recent near PMP events in Virginia are in line with world record rainfalls. Given these concerns, the Virginia Beach Department of Public Utilities decided to undertake a detailed study of the impacts a catastrophic tailings release could have on the city's water supply. We were particularly interested in the concentrations of radioactive and toxic substances in the watershed following the release, and how long elevated levels of these contaminants would persist. To estimate the potential impacts of a uranium mill tailings release on the downstream water supplies, we contracted with national subject matter experts and employed state-of-the-art computer models. Our consultants were specialists from Michael Baker, Inc., a leading engineering firm with decades of experience in water resources engineering and flood risk management. Model development was performed by the National Center for Computational Hydroscience and Engineering at the University of Mississippi. In addition, at the onset of the study, we retained a peer review panel composed of experts from academia, government, and industry. The computer models we used are capable of simulating the flow of water in rivers and reservoirs, the transport of sediment and tailings particles, changes of river cross-sections and bed elevations, as well as the chemical behavior of various contaminants. We simulated the impact on and transport of uranium, as well as two primary radioactive decay products, radium and thorium. These contaminants are regulated under federal and state drinking water regulations, and their radioactivity is measured in picocuries. The maximum contamination level for radium in drinking water is 5 picocuries per liter. Likewise, the maximum contamination level for all alpha radiation emitters is 15 picocuries per liter. Both thorium and radium are alpha radiation emitters, so their combined simulations were used to gauge compliance with the regulated limits. Note that there would likely be more than these two alpha emitters in the uranium decay chain, but we limited the analysis to these two primary daughter products. Therefore, the simulation results can be considered a lower estimate. Uranium in itself is regulated for drinking water at a concentration of 30 micrograms per liter due to its kidney toxicity. The initial research revealed that the amount of tailings released is a key factor in the concentrations of contaminants arriving downstream, so we selected a conservative scenario based on available information of the size of the proposed tailing cells as well as on historical tailings dam failure data. We estimated that approximately 1/3 of one tailings cell, or approximately 750,000 cubic yards, would be discharged to the Bannister River. Note that VUI plans multiple tailing cells with up to 2 40-acre cells operating simultaneously. To determine the effects of stream flows on the transport of the contaminants, we selected two scenarios. We ran simulations with the tailings release followed by either a 2-year wet period or a 2-year dry period. For both scenarios, we utilized actual stream gauge test center data as boundary conditions in the model. Because there's considerable uncertainty regarding the chemical behavior of the contaminants used in the model, we also ran repeated simulations with a full range of potential solubilities for the contaminants. Next, you will see the results of the simulations as computer animations, showing the transport of contaminants under different hydrological conditions through Carr Lake and Lake Gaston. The data shown represent the concentrations of radium dissolved in water or associated with particles suspended in the water column. The first animation shows the transport of radium through Carr Lake during a wet period, when stream flows are high and lake levels fluctuate widely. The top left portion of the image is the convergence of the Dan and Roanoke rivers. Flow of water proceeds from left to right. The graphical scale indicates radioactivity in picocuries per liter. As a reminder, the allowable drinking water limit is 5 picocuries per liter, which, on this color scale, would correspond to a light blue color. So any colors warmer than light blue indicate water contaminated at levels exceeding the allowable limit. While the animation is running, the elapsed time since the tailings release is displayed beneath the image of the river. Within a few days, radium levels increase rapidly to hundreds of picocuries per liter, and within a week, the slug of contaminated water coming from the Bannister River reaches the outlet of the lake at Carr Dam. Because Carr Lake is operated for flood control, the water level in the lake will increase rapidly to accommodate floodwater, which causes contaminants to be transported into the tributaries of the lake. Because of the high stream flows contributed by the Roanoke River, however, the contaminated water is rapidly diluted, and radium concentrations subside below the drinking water standard within a few months. The colored pulses towards the end of the animation also illustrate that subsequent high stream flows remobilize more contaminated sediment from upstream and transport them into the lake. This animation shows the transport of radium through Carr Lake during a drought period, when lake levels and stream flows are low. A few days after the tailings release, radium levels increase rapidly to 20 picocuries per liter or higher. It takes approximately 2 months for the slug of contaminated water to reach the outlet of the lake. During drought periods with lower water levels, Carr Lake essentially behaves like a wide river, with little to no transport of the contaminant into the tributaries. Approximately 1 year after the tailings release, as higher stream flows cause lake levels to increase, contaminated water is migrating into the southeastern branch of the lake. The colored pulses towards the end of the animation also illustrate that subsequent high stream flows remobilize more contaminated sediment from upstream and transport them into the lake. This plot illustrates the time-dependent radium concentrations after a tailings release at the Clarksville water intake at Carr Lake. The horizontal axis shows the time elapsed since the tailings release in days. The vertical axis shows the radium concentration in picocuries per liter, where each increment represents a 10-fold increase. The two colored bands represent the two hydrological scenarios, wet and dry period, and the upper and lower limits of each band represent the range of solubility of the contaminant. The horizontal red dashed line indicates the maximum contaminant limit, or MCL, of 5 picocuries per liter for radium. During the wet period simulation, shown by the green band, radium concentrations subside within 30 days below the MCL after an initial peak that exceeded the MCL several hundred times. The lower concentrations during the remainder of the simulation period are primarily due to the dilution of the contaminants by the larger stream flow volume. The red band indicates that during a drought, concentrations decrease below the MCL within 3 months following a potential tailings release. Subsequently, however, short periods of high radium concentrations above the MCL may occur when higher stream flows remobilize contaminated sediments from upstream. This graph shows time-dependent radium concentrations in the southerly branch of Carr Lake near the water intake of the city of Henderson, North Carolina. It illustrates that even after nearly 2 years following the tailings release, radium concentrations can exceed drinking water standards at locations far from the main channel of the reservoir. This animation depicts the concentrations of radium in Lake Gaston following the tailings release during a wet period. Note that the color scale ranges up to 5 picocuries per liter. As with Carr Lake, The slug of contaminated water reaches the outlet of the lake within 2 weeks. Unlike Carr Lake, the lake level is maintained relatively constant, even during flood events, and therefore the contaminated water is not pushed immediately into the branches of the lake. However, the small level fluctuations of around 2 feet cause eventual dispersion of radium into the tributaries. After about half a year, it reaches a maximum of 1 picocurie per liter at the city's pump station intake on Pea Hill Creek. Contamination persists in the tributaries throughout the simulation period, albeit at levels below the standard. During a drought period, contaminated water reaches Lake Gaston approximately 2 months after the tailings release. The highest radium concentrations reach the outlet after another 2 months. As before, small variations in the lake levels cause dispersion of contaminated water into Pea Hill Creek. Radium concentrations are much higher during the dry period. They exceed the MCL at the city's water intake after approximately 7 months and persist for nearly 2 years after the tailings release. Note that this animation represents a scenario during which the city's pump station was operated. As shown in a following slide, the city's water withdrawal can have an impact on the radium levels in Pea Hill Creek during dry periods. This graph shows time-dependent radium concentrations at the outlet of Lake Gaston, and it illustrates the large impact that stream flows have on the concentration of radium. Within 100 days following the tailings release, dilution causes the radium levels to decline below the drinking water standards during a wet period. A considerable delay and higher concentrations would be experienced during a dry period. The contamination of Lake Gaston would persist for up to 500 days, or 16 months. Our simulation also revealed that the operation of the city's pump station has no discernible effect on radium levels within the main channel of the lake. In this graph, we overlaid the radium concentrations for scenarios with and without water withdrawals using the Lake Gaston pump station. The solid color bands represent the scenarios without pumping. The band without a fill color represent the data with water withdrawals. As the computer animation showed previously, the contamination due to a tailings release during wet years remains below the maximum contaminant limit for radium. However, during dry years, radium levels exceed the MCL approximately 200 days after the catastrophic event, and the operation of the pump station results in earlier arrival times and higher concentrations in Pea Hill Creek. More importantly, contamination of the tributary results irrespective of whether the Lake Gaston pump station operates or not. That is, transport of contaminated particles into Pea Hill Creek appears to be primarily caused by the varying lake levels. These last graphs show the radium concentrations upstream on Bannister River near the town of Halifax, Virginia. Due to its location in the vicinity of the mining site, approximately 30 miles downstream of Coles Hill, radium concentrations remain consistently above the drinking water standards by orders of magnitude, regardless of stream flows. Even though the model simulations were run for a 2-year time period, the lack of a decreasing trend in radium concentrations suggests that the contamination will persist for the foreseeable future. This becomes evident when examining the contaminant mass that remains within the watershed sediments 2 years after the tailings release, as shown in the following table. From the data presented in this table, we can conclude that the impacts on Lake Gaston were due to only a small fraction of the contaminants that were initially discharged into Bannister River. The vast majority of the contaminants, between 54% and 84% by mass of radium, thorium, and uranium, are being retained in Bannister River. As the computer animations illustrated, flood events can remobilize the tailings particles from the sediments and move them downstream long after the catastrophic release. In conclusion, our studies show that the concentration and duration of contaminants in the watershed is greatly dependent on whether the catastrophe occurs during a wet or dry period. Contaminants could pollute the watershed from a couple of months up to a couple of years. In all scenarios, however, contamination levels would be above allowable limits for some length of time. Additionally, since the vast majority of toxins remain in the Bannister River, there will always be a threat of occasional floodwaters raising the contaminants beyond allowable limits into the foreseeable future. For the city's water supply, we know that contaminants could exceed allowable limits for up to 16 months. These contaminants will work their way to our pump site whether we continue pumping or not. But having to shut down our pumping operations from Lake Gaston would cause extreme water shortages for all of Southampton roads, severely damaging the health, economy, and viability of one of Virginia's most populous regions. Although the probability of an accident may be small, the consequences of an accident would be enormous. For the City of Virginia Beach, it simply isn't worth the risk. To learn more about the City of Virginia Beach's studies and position on uranium mining, please visit vbgov.com.